let's begin with antiderivatives. So we spent the whole quarter in calculus 1 looking at derivatives, right? And so, well, let me mention one word for you guys a little bit right here. Derivatives. Now, looking back at derivatives, all of the derivatives work. You guys learn derivative rules and all of that, right? But the derivative belongs to one branch of calculus that's called differential. Okay, differential calculus. So this is traditionally or formally what the whole calculus 1 course is all about. You learn all techniques about differentiation. The term I introduced for calculus 1, right? It's called taking the derivative is differentiation process. Okay? And so the whole calculus 1 that you guys learned, it was all about differentiation work. That's why it's called differential calculus. Sounds good with that? Okay. And then so derivatives was the big work. It's the only work throughout the quarter. We started out with limits, but we use limits as a foundation for calculating derivatives. And so now you've been so fluent, right? Hopefully, so fluent with taking derivative and finding derivatives. So now let's look at antiderivative. Antiderivative. All right. You see the prefix again? Anti. So, but don't worry about the name, whatever I'm about to introduce, okay? Like in my style of going through the class or of any class, okay? I'm not going to just get straight into telling you what it is, but this is how we learn what it is here. Let's say we got a function, a function f of x, okay? This is a function given. It's just a promoting property here. Let's say it's an x cubed. Okay? So I want you to find a function. Find a function capital F of x. It's a different function. I want to find a function f. The capital F of x. This is f of x. Different things, right? So find a function capital F of x such that, or satisfying that. Let me use that term here. Satisfying that. This is the requirement for here. I want the derivative of the capital thing right here to be the x cubed. You guys following? Okay. That's a new challenge for us. Okay. So we're not finding the derivative of that x cubed function. Okay. We're not finding the derivative. We want to find out, hey, what function is it, right? What function that is giving me x cubed as the derivative. See what I'm saying now? So this is just a formal way of how the problem is worded, but then sort of like the way to understand it. The way to understand that, right? What is the function? What is the function that has f of x equals x cubed as its derivative? See, this is the kind of question that you're putting in your mind when you're doing this problem. See what I'm saying now? We want to find out, so that's what capital F that we're looking for. So we're looking for capital F. But the way, as a thought process, right? What is the function that has lowercase f equals x cubed right here, being its derivative? See what I'm saying now? Okay? So, and of course, there's just the first day right here, there's no methods that I taught you guys yet. So, rely on your own understanding about calculus 1 right there. So the function we're currently at. So right now you treat this as a derivative, right? A derivative. So the derivative already arrived at x cubed. So what was that function that has x cubed as the derivative?
Should we just speak or?
Should we what?
Should we just speak or do we need to?
Yeah, just tell me what you have.
1/4 x to the power of 4 plus 8.
So allow me to hold on to your 1/4 in front, okay?
Yes.
But see, what makes sense naturally is a power of 4. You guys see that? Because a major thing we've learned about derivative is that when you take derivative, then the power goes down. See what I'm saying now? When this was when it was a fourth power, taking the derivative, and yes, we bring the power down as a coefficient, and then the power we use by 1. That's why we get something with the x cubed. Sort of agree. See what I'm saying now? So I agree with x to the 4th. And so now, the reason I pause him on 1/4, which is where, but even though I agree with him, the reason it has to be a 1/4 now is because, see, if we just stop as x to the 4th only, taking the derivative, is it giving me just simply x cubed? No, taking the derivative gives me 4x cubed, right? But the real derivative we want here is x cubed. See what I'm saying now? So that's why the trick here is that you have a 1/4 in front. So you have a 1/4 in front so that when it's a 1/4, right, in front of your function, then there's a 1/4, and you multiply down with that, and the 1/4 cancel out and gives you the x cubed. See what I'm saying now? So there's really one same problem, but searching for the answer in the mind process. There are two steps here. See, the power, it's a power function in the end, right? You guys can call that name like that. It's a power function. So taking the antiderivative, first you got to raise the power. See what I'm saying now? We raise the power, so it was 3, being the derivative, raising the power is going to increase by 1, right? We're going to increase by 1. But then simply increasing the power, we're going to need to multiply with a coefficient 1 over that new power here. See what I'm saying now? To compensate for whatever, when you take the derivative, it's going to have to cancel out and come back with the actual one that we desire. Okay? So yes, I agree with 1/4, but I try to add it with that explanation. Yeah. You guys with me on that? Okay, and so it looks like you already learned something. Here's how we're formulating it. Because at this point, yes, Calc 2, somewhere at the beginning of Calc 2, you guys still already learned something here and there outside. I want to set you guys into that formal learning and the thought process of where that came from. And because I don't want you to speak out of formulas or things like that, but you got to have a solid understanding of where the formula came from. So the function we have for now, and let's start putting for ourselves a table like this. Okay? So if you got here you got on one side it's the function itself, right? And then yes, this function. Then here's the antiderivative. All right. And then if function, and it's just the way that the majority of mathematicians worldwide are agreeing right there that if we use a lowercase f to be the function, then the antiderivative version we're going to use a capital F. Okay, sounds good with me on that again. All right, so that's one thing. So now if your function is being some x to the n as suggested, right? The problem here I was starting out with x cubed, but generally I hope you guys learned a generality from this problem that it's a power function. See, I could have asked the problem right in the beginning to be, x squared or x to the 5th, right? It's a power function. These are all generally some x to the n power. Sounds good? Okay, and so from what we learned through together, then when your function f of x is an x to the n over here, then you're taking the antiderivative. It's going to give me f of x to the n plus 1, we increase the power by 1, right? And then we multiply that with the coefficient 1 over n plus 1. Okay? So it seems like we found our first rule right there. Right? But then there's still more to that. And we didn't get all of it yet, right? But right now, we're building it up as we go with that. So I'm going to come back to that table and put in some more details. Let's go back to the same problem. I didn't close it down yet. Let's go back to the same problem. And the answer was 1/4 x to the 4th. So starting out with just that same search again, right? We got a function being x cubed, but then we were searching for the capital F prime of x. And so now capital F of x, right, is according to your work here, you found it, right? It's 1/4 x to the 4th. The question now is, what about something like this? 1/4 x to the 4th plus 3. Can this be that capital F as well? Just think of, now what I'm asking, because remember the goal here, all I'm asking is some function so that when you take the derivative, right? Some function so that when you take the derivative, you end up with take the derivative to end up with x cubed. Take the derivative of this guy right here. Of course, this guy is not the same guy as the simple 1/4 x to the 4th, right? We're taking the derivative here. Is it going to give you x cubed? Simply just that. And of course, taking the derivative here, we already knew that it gives us x cubed, right? See what I'm saying? No? So what about another quick scratch one right here? 1/4 x to the 4th, and then you minus 1,000 right here. Right? Is that going to be another one that satisfies this thing that we're looking for? Okay. And so let's take the derivative, because constant term, right? In your work of finding derivative, it's going to be just x cubed. So we got all of a sudden we start realizing, hey, there are so many of them. There are so many of them. Just to find an answer to this question, we want to find that function. And I didn't even use the formal name yet. Maybe on that table there I called it antiderivative, but I didn't give a formal definition yet, right? But so far, just to find that function where it gives you the derivative to be x cubed, we found 3 different candidates, and now expectedly there are a lot more out there, right? So generally speaking, when you're doing this kind of work right here, then it's not just one function. It's going to be that main function, but you're going to have to add with a constant c over here. That's solving with that, okay? So the c here is back on my other board. The c is just like, it could be a +5, it could be a +10, it could be a -1,000, right? We adding a constant c. Now, in case I haven't mentioned this at any time at all, but in my understanding, algebraically speaking, a subtraction is also an addition. We're adding a negative sign, a negative value with that. So in algebra, when it comes to adding and subtraction, really it all breaks down to just one operation. We're adding. What matters is we're adding a positive number or we're adding a negative number. See what I'm saying now? And the same with multiplication or division. Because 2 operations distinctively, it looks different at first, right? But in the end, it all just really one operation with that. We just multiply. We multiply by the number itself, or we multiply by the reciprocal of the number. See what I'm saying? Huh? So it's either just adding or multiplication. So now at this point, we got something written down on that table. Let's give it a formal definition of what it is to be an antiderivative. And then for that table, I'm about to, I wrote a little bit there. Make sure you leave some more space because I'm going to come back and fill in some more into that table. Okay? But so, this is the definition. All right. That x, right, be a function. Just any function. Okay. So an antiderivative, let me write it in red ink here. Antiderivative of the function f of x. And formally we use the symbol capital F of x. You know what I'm saying, no? An antiderivative of x is a function satisfying. We just want to find that big F, so that's the derivative of big F equals F. That's what matters. That's how we'll be finding it. Okay? So yes, go ahead and spend some time writing it down right there. We have a formal definition. Now when you're done writing it down, you can see, you can have a closer look and you can see the intention of my wording right here. You can see when it comes to antiderivative, a lot of times I'm going to say an antiderivative because there are many of them, right? So whichever one that you found is only one among many others. Okay? So as a matter of fact, antiderivative is more like a whole family of functions, a whole family of functions that satisfy this requirement. Okay? See what I'm saying? No? Right. And so a couple more terminologies here. You see, so starting with this, f of x equals the x cubed that I promoted, right, in that beginning problem. Okay. Capital F of x being a 1/4 x to the 4th. You guys agree? Okay, and then yes, it was this word, and then I just tried to put in some further explanation as a thought process, right, to get that really enforced. But then I made you guys realize that aside from that one, there's a whole family. So it's not just 1/4 x to the 4th. But as a matter of fact, it should have been a whole family, like different by a constant c with that. See what I'm saying? No? And so that's why that is an antiderivative, and any of these is an antiderivative, right? And so this special version right here, this special version where it's constant 0 right there, right? A lot of times people call that the main. So this is here, it's called the main antiderivative. Okay. So a lot of times just that special version where constant c is a 0, we call it the main antiderivative. Sounds good? And then the whole family here, right? The whole family here would generally be written as a plus c right there. Yes, you call that. This is the general antiderivative. Okay. So really, the general antiderivative here is not just one function. It represents more like a whole family of antiderivatives out there. See what I'm saying? That's just the way how it happens right there. So I'm introducing these terms so that in case you hear other professors, or sometimes you have to look up on YouTube videos, right, for some extra learning resources right there. And you may hear those guys over there that they're using those terms. That's what they are. Sounds good? All right. So now at this point right here, you guys can have a sense about why we call it that antiderivative, right? What does the prefix anti mean?
Opposite.
Yeah, it's opposite, or we're reversing that work, right? We reverse that work. Again, we're reversing the work of finding derivative. So you spend the whole time in calculus 1, right, learning how to find derivative. And now we think about we already had a derivative, right? We find out ways to reverse that, and we find the function before taking the derivative. Okay. I'll do that again. Okay. So that's why back to this particular table right here. Back to this table right here. This is the famous people, and this rule right here, you guys already learned one rule, and then still, I'm gonna shortly close the rule for this. But there's gonna be more special rule, but this specific rule right here is referred to as the power rule. Okay, this is a power rule. We're taking antiderivative. So when any time that your function is a power function, just like that, right? Taking the antiderivative, you simply raise the power by 1, right? And then multiply with the power with the coefficient 1 over n plus 1. But then don't forget add c. So for any of the beginning students into this, and it's actually not only for the beginning students. Anytime that you are doing antiderivative, make sure you have the add c right here, unless specified otherwise. There are some problems that you may be instructed to skip the plus c like that. Okay, but for the big majority of time, you gotta indicate the plus c. Look at that like that. So when you're taking your exams or whatever, your written work, and I don't see your plus c, I have my legitimate reason to take away a couple points and stuff like that. See what I'm saying? It's very important that you indicate. Because skipping that means that you're only talking about the main antiderivative, right? But a lot of times I'm asking for the general antiderivative. Sounds good, then? And then this rule here still has a little going on. This rule still has a little going on right here. So we're not quite complete with that rule yet. So let's go back to that antiderivative right here. We learned it. We learned what it is. We got a definition. So let me immediately take you guys into an example where you're going to even have better experience. All right. So let's now call that example 1 here. So, and right now you gotta also keep in mind, in case you already learned somewhere here and there on YouTube or on whatever, people use this kind of symbol, okay? For a formal class, when you're learning, let's say that for later, the only symbol we use right now is That version right here. Your function is lowercase f, right? Antiderivative, I'm going to use a capital F. That's what it is. Can you guys agree with me on that? I mean, historically speaking, there's a whole reason. It's not just like, hey, here you go, like the YouTube people telling you, hey, here you go, this is antiderivative. It's not really just that. See what I'm saying? Now, you may have seen some of that already because these days, internet is so available, but you got to align your learning with what's going on here. So, find the antiderivative. Okay? With capital F of x is the antiderivative would be given for each given function f of x. Right? That's why clearly this is the antiderivative version and this is the beginning function version. So, what about when your function is how about an x squared times cube root of x squared times the cube root of x. I mean, the only rule I introduced for you guys is that power rule effect, right? It has nothing to do with multiplication between two functions. I mean, obviously, your algebra instructor is going to tell you that this is a product of x squared, right, times with the cube root of x. See what I'm saying? It's a product. But sadly, we didn't learn anything about a product yet, right? We didn't learn how to handle the finding antiderivative of a product. And so, here's how we treat it. The algebra is so important. You never look down on algebra. Okay? So this is before we find the antiderivative, you're going to be write your function here as x to the power 2 plus a 1/3. Okay? We call that the cube root, right? It's a 1/3 power. You guys follow? Okay. And so the same as x squared times the x to the 1/3 power. And that's why you need the rule of algebra. So right now, it's not the antiderivative word. It's just the rule of algebra. It's indicating that you need to add these two powers to come up with a final power. See what I'm saying there? So that means your function here really is in a power form. It's going to be a 7/3. You guys agree? Is my math doing all right? I make these silly math mistakes all the time. Okay? But then that's how you rewrite your function in the power form. And that's going to be the way forward for a lot of problems later on, like that before we learn a new rule. See what I'm saying? Now, anytime you have a problem given it, your only plan is to rewrite. Somehow you find your way to rewrite your function into a power form. An x to the n. See what I'm saying? Huh? So now this will work. So now that leads to, right, your antiderivative now. So now it's the easy work is going to come out. See? You go x, right? 7/3, you're going to, and it never hurts to write it down right here. 7/3 plus 1. This is the antiderivative work. And you multiply with 1 over 7/3 plus 1. See what I mean? Okay? It may slow down your process at first. And then eventually when you're fluid enough, it's going to fly. See what I'm saying? Huh? Okay? So, but don't forget plus c. So that was the main, and then now the whole antiderivative is any of these with the plus c. Right. So now let's do the math here, a little bit of math. At the end, capital F of x right here is what? So 7/3 plus 1, right, is making it a 10/3. You guys agree? Okay. And then 1, so supposedly this here, the denominator is a 10/3, right? So multiplying, 1 over a 10/3 is making it a 3/10. You guys agree? Okay, plus c. We found an answer. So it's got a lot of thought process in it, right? And work and the reasoning for that. Sounds good? But the only plan here is to make that, a power function, the form of a power function, so that we can apply the only rule we've learned so far, the power rule. Sounds good? Okay. So let's continue. X cubed times the square root of x. So let's have some fun writing it down together. I'm purposely writing something here so that after you learn how this works here, you can also think about the other cases. But now, you see, Again, we got fractions, right? We didn't learn anything to handle directly with fractions. We got a 1 over, it's a fraction, but now the only thing we can do right now is to rewrite your function. I'm talking about rewriting your function as a power function. So first of all, let's leave the 1 on top for now as the same way it is. But x cubed plus the square root x in the denominator, again, you learned that from the previous problem. So now you can write it as a x today. So 3 plus 1/2, right? For the power right here, that's making it what? 7/2. That's great. So in the denominator, we turn that into a power x to the 7/2. But then the function, the fraction here is a 1 over x to the 7/2. So that means further algebraically, you can further write that as an x to the negative 7/2. This is where you successfully turn your function into a complete power form. You get that? I'm talking about a complete power form. You only, when you arrive at, some x to the n power, right? N doesn't have to be a whole number like x cubed, we saw it out. See what I'm saying? Now you can go ahead and do your antiderivative thing. Your antiderivative thing, right? Capital F now is ready. Find out, once again, your power of the x, you go negative 7/2 plus 1. I highly recommend doing this when it gets to the negative power like that. Because a lot of times, I keep having students mistakenly, they think plus 1 as in a sense of increasing more negative. But increasing more negative means from that negative you subtract 1. See what I'm saying? No? So plus 1 here, you actually reducing the negative of that. That's why it's write it down at first. Write it down at first. And then yes, 1 over, and then negative 7/2 plus 1 right here. Sounds good there? Right? And then plus c. Alright, so now your function is ready. Your antiderivative is ready. The antiderivative, capital F of x, right? So minus 7/2 plus 1.
Negative 5 over 2.
Okay, negative 5/2, yes. So x to the negative 5/2, yes. And then, of course, we have let me put that in, because it's 1 over negative 5/2. You guys agree? Okay, plus c. All right. So now, capital F of x here is going to turn into a negative 2/5, right? Algebraically, times x to the negative 5/2 plus c. So, at this point right here, it's just a matter of the final expression. A lot of times, including me right here, I'm okay with this way of how you writing your final answer should be in a negative power. A lot of times, it's okay with that. But be aware, there may be problems that are assigned by other professors where they have an indication that, rewrite your expression so that it's free from negative powers or anything like that. And make sure you know how to put that in the denominator. Okay? And then there could be problems that make sure you write your final answer, free from the fraction power. That means you're going to have to put it in roots. Things like that may happen. Okay? So be aware of that. But right out of the box, this is your final antiderivative already. Sounds good? All right. So one more thing to put into your little bucket reference here. So we've learned that nice trick, right? Even powers in the denominator, we turn that into a negative powers, right? And then we learn how to handle roots and all that as fraction powers. It all works with the rule we've learned so far. So what about this deadly situation here? Just think, like I said, maybe you have learned something already before the class, but that's not the point, right? The point now is to think about, can we use this rule here, this power rule here? Right? The same trick we've been doing. Well, I have a reason to write this as x to the negative 1. You guys follow it? Okay? Because sometimes you gotta be pointed into some direction where you got stuck, and then you're gonna appreciate the formula that you love. Now, that means you are in complete power form, right? See what I'm saying now? So now, searching for that antiderivative rule. See, don't we agree? Didn't we learn that the x to the negative 1 plus 1, right? We add the power by 1, right? And then we go to 1 over negative 1 plus 1, and then plus c, okay? See what I'm saying now? Okay? What's wrong with this work? For this only problem?
1 over 0.
That's right. You got a 0 right here, right? We just can't divide by 0. You see how many you guys are in math now? You can't count 2, right? And did we learn how to divide by 0? We still have not learned how to divide by 0. Okay? You go to count 4, Will people there learn how know how to divide by 0? They won't know how to divide by 0. Okay, we'll never know how to divide by 0. So that's why now going back to this rule, that remaining detail I want to add in right here is that this power rule only works for, it's only going to go into this antiderivative for n other than -1. Any other n value will work, but not n equals -1. See what I'm saying now? Alright? So at this point, other than the definition that I formally given out, right, in the earlier lecture, we didn't really learn any methods. Basically, the only goal, keep in mind that we're trying to find a way to undo a derivative, right? So anytime you're asked to find an antiderivative, it just means that, hey, we treat that as a derivative already done, right? But what function before we found that derivative? Giving me this here as the derivative. Okay, so what function was it? Right? Giving me 1 over x to be the derivative. So remember, the power rule we've learned doesn't work because here obviously it's x to the -1, right? It failed. I mean, it falls right out of that case we want to exclude out. It falls right into that. So that's why I don't use the power rule. But we do know a way to undo this, right? What function? So this is where you bring back your calculus 1 learning really. What function has derivative being famously 1 over x? Yeah, ln x, right? So yes, that is true. So now, there's one thing that I need to mention a little bit here. So back in the days at count 1, right, it's easy to, yes, ln of x, the derivative of ln x is 1 over x. See what I'm saying now? Okay. But now, when you take the antiderivative, it has there's a certain requirement here. Now, when we're just simply looking at natural log of x just to find the derivative, and nobody bothered much about the domain of that. But you guys should have also learned that in your pre-calculus that anytime you're looking at a logarithm, right, the domain gotta be only positive. The domain for a logarithm, any logarithm, it's not only just natural log. See what I'm saying now? So think about in the role of taking derivative of logarithm. So when you are given a logarithm and asked to find the derivative, then everybody is assuming that you're in the proper domain, having a positive x, right? Having a positive domain. But now on the way back, where I'm talking about f of x here being 1 over x. The domain could be the domain. Think about this function here. The domain could be in interval notation anywhere from negative infinity and 0, between anywhere between negative infinity and 0, and union with that 0 to positive infinity. Basically, think about the whole line of numbers. The domain for this function really is 0 is here. We exclude out only 0. We take everywhere else. That's the domain for 1 over x. See what I'm saying now? And so for that reason, be extra careful really, be extra mindful really. When you take the antiderivative, yes, it's easy enough to think that it's natural log of x, right? But here's the thing. When it comes to the antiderivative, we cannot take all x because the domain of the beginning function here really can take anything except 0. But now when you make that become the logarithm here, you have to force that into absolute value. You guys follow with that right there? Why is that? Because we want to ensure that, yes, the absolute value here means no matter what x value we take, right? But when it becomes the logarithm, it's only the logarithm of the positive x. Am I making sense like that? Okay. So the absolute value of x purposely force all x values to become a positive value before taking the logarithm. Okay? So there's a major switch right there. So back in the derivatives day, it's easy to understand that no one ever bothered mentioning that much, including me. I don't think I mentioned that to any one of you guys, right? But now on the way back, when we find an antiderivative, you got to be extra cautious. Your logarithm got to be natural log of x. I mean natural log of absolute value x. Sounds good? That's like that. And then eventually, when you working often enough with that, you will see people just commonly refer to log of x, but that's kind of subconsciously means the absolute value of x already. Okay? So later on, when you work with a lot of problems later on, when things get intense and a lot of antiderivative words, all of a sudden just boom, boom, boom coming at you, right? And a lot of times we may go lose with the precise notation like this, but that's you gotta automatically understand that it's a logarithm of absolute value of x. Okay? But right now at start, I want to set that foundation for you guys. Okay? And then don't forget, there's that. Let's see. Sound good? All right. And so with that deserves its own attention. So now I can write it on here. In our table here, it's just another special rule over here. So the power rule, so this rule itself, yes, it handles power function. But then we can specifically call it as the power rule. It's not the power rule for derivatives, it's the power rule for antiderivatives, right? And so now the next one, it's not even a rule, it's just one specific thing on its own right here. The function here is a 1 over x, right? Sounds good? All right. And then the antiderivative here comes out natural log of absolute value of x plus c. And that takes care of this specific case again, right? We overcome that. Right. So let's look at some notation. So right now I only want you to understand this. Everything here I'm showing you, what I'm about to show here, I just want you to understand that simply as a notation. So you see the work here, it has been since our beginning day, we've got a given function, right? And then we are asked to find the antiderivative. So we use that notation to indicate antiderivative. So this is okay, understood, right? Understood as antiderivative. Okay, right derivative. Antiderivative of f. So it's been like that. You know, the lowercase version is f, the capital case version, right? It's antiderivative. So you got lowercase g, capital G means antiderivative. But see, that sometimes will cause problem because eventually we're gonna run out of letters, right? I mean, naming function f, or sometimes we name function g and all that. We're gonna eventually run out of letters. And so, I'm talking about a better notation. So look at the whole wording right here. It's actually an entire word instruction right there. You got a given function and you're asked to find the antiderivative, right? So it's just a problem with mathematicians. We don't want you to write too much worded thing right here. So with the given function, now I introduce for you one symbol as a whole package here. This symbol together with the thingy right there. Okay? That symbol, I don't even want to say anything about the actual name. We're going to learn the real name later. Right? If you hear somewhere, YouTube people call it the interval sign, forget about it. Think about your roll back at the starting point again. It's a symbol indicating. And so for now, I want you to understand. This symbol always comes together with the D thingy right here as one package. See what I'm saying? That's why I'm circling that in red. And so this symbol here really replaces an instruction. When you see that symbol together with the D right there, it tells you that, see, find the antiderivative. See what I mean? Antiderivative. Replace all of that wording right there. Find the antiderivative of function f. You guys all with me like that? Right? That's why it's, right now I want you to understand it that way. Because technically, in a very traditional calculus learning right there, your instructor back then, if you were taking this about 20 years ago, when it was my time, I was never taught to use this until halfway of the quarter, when you formally get into learning what that is. But now, in these days, because life is always rolling fast, so we kind of cheat around, so we kind of violate that order a little bit. But it's officially allowed that, hey, you can only at this point think of this as a one symbol. And this symbol is a replacement for this entire worded instruction. When you see, so now from now on, when you see a function g, right, whatever lowercase, capital case, but you see this symbol attached to it, you see what I'm saying now? And that's now is an instruction. It's asking you to find right, the antiderivative. You see that? No? That's what it is. Okay? On the antiderivative of, see, what function in regarding to that function g. Okay. You attach a symbol, you copy and paste that symbol, right, and attach it to a function like this. Right? Put that on top of a function, and that gives you a complete the instruction. Hey, find for me the antiderivative of that function. Does that make sense so far? Okay. And so, and a little more. The D thingy right here also, the D thingy right here, I want you, now I'm introducing that symbol. There's also a whole intentional, why is it a dx here, whatever. You see, your function here, and right now, like I said, I only want you to think of this as a notation, right? So as far as a notation and that a notation representing an instruction, then your function here primarily is in terms of x, am I correct? X is the main variable inputs that you name your variable of the function, right? And so it has an association. The dx here is telling me that, hey, you treat x, you're targeting x as the variable, right? And then you take the antiderivative in respect to x here. So this here means the dx here really means it's not just there for fun, right? It's there because in respect to x. See what I'm saying, huh? In respect to x. Or what exactly does that mean in respect to x? Well, it means we're treating x as the variable. Right? We're treating x as the variable. You don't see much of the impact right now yet. I'll point out why it's so important to have the dx, the dy a little later. I mean, I'm talking about you guys are here to learn the formal stuff. Because it's not like the DIY that you hop to YouTube and you hop onto YouTube and people tell you, hey, here you go, that's the integral and move, you get it done. That's not how it works. You got to learn the whole idea of why you're coming up with that, so that you can have that flexibility to apply it anywhere. See what I'm saying? Okay, so the whole reason why I spent so much time beating around the bush with that symbol, because so here's the thing. Let's say at this point of your learning, you guys are experienced to see that, hey, you got, let's say you got a mx plus the dy, an expression, right? As far as variables, which one of them is the variable? Tell me. Which one of those is a variable? It's an m right here, by the way, in case you couldn't recognize my writing. So m times x plus b times y, right? Which one of them is a variable? Any one of them. Agree? They're just letters. Right? Because the m can be whatever, right? And then the x can be whatever value. See what I'm saying now? Okay? And so that's why now if you're talking about this here as a sum function, and I'm not even sure which one of these is a variable, that's why I'm just leaving that kind of open. You got the idea? So now, with an expression like that, which is looking so dangerous, now with this symbol, that's your function, right? See, I'm telling you to do this. That tells you, hey, out of this function, I want to find the antiderivative of this, right? But what do? We treat only that as a variable. That guy now is playing the role of a coefficient. You see what I'm saying now? Like a 2, like a 5? Am I making sense? And then this guy here, 2 variables to involve, but the indication here, the instruction here is telling you that you only need to worry about the main variable here being the x. So what does that whole guy do right here? Constant term. Like a 5 or like a 10 being there. Am I being clear? And that's why for that case right here, yes, see? And we didn't even get to that, the for extent yet, but eventually you're gonna get there. For now I'm cheating around a little bit, but it's gonna be m over x squared over 2. Right? And then plus dy times x again, plus the c, and we'll get to the little bit more of that because I didn't even explain to you what do we do when we have 2 terms added, but we'll get to that. But the point I want to mention now is, see, an expression out of nowhere like that, right? It has so many variables involved, but what this d thingy right here indicates for you the targets, the main variable being targeted here is the x. Sounds good? And so for that reason, think about it again. You have to start thinking outside of the box here. Okay, my writing is getting a little busy. Same thing here. I want to find an antiderivative, right? But you see the idea now? Right? So this time the exact same expression, but I'm treating b as our main targeted variable. We're targeting at this guy being a variable, and this whole thing here is constant. Make sense? Okay, and this thing right here is a coefficient. And then only the b is the variable that matters. So b is the power of 1 or whatever, right? So we raise the power by 1 and we divide by 1/2. I mean, we multiply by a 1/2 according to that power rule that we've seen again. Okay. Sounds good with Africa? All right. And so once now we have learned that new formula, that new enhanced formula right there. And so allow me to modify this table. So in this table, a better way of writing that. Okay. So it's sort of like yes, it's called power rule and all that, right? But so, it's kind of weird writing like this. But so formally, that's you got a function, and we run into antiderivative, but then all in one revised version, right? This is how we're writing it. See, taking the antiderivative of an x to the n in respect to x. See what I'm saying? No? That finding the antiderivative gives you 1 over n plus 1, right, times x to the n plus 1 plus c. That's how it works again. Right? And then this is, yes, this rule again is only working for any any power n other than -1. So it's sort of like a revised rule like that. Sounds good? And this is the rule that actually, as a matter of fact, you grab any textbook, your active calculus textbook that you guys are using in any other textbooks, you're going to see that version like that. Okay? So what I gave out at the beginning here is just an explanation of how the rule works, but in the end, for short, right? That's how it is. Sounds good? That's why it's called the revised version, and it's for textbook. Okay? And so in the same way right here, now you can revise this. See, the instruction says that we want to go from this given function, right? Find the antiderivative in respect to x to arrive at this, right? So you will see in your textbook that, see, on the 1 over x function, taking the antiderivative on that function, right? It gives you the natural log of absolute value of x plus c. Nice and easy. Okay. That's how you are revising those rules again. Okay. Let's now look at a few other ones, a few other special ones. Just a quick review on your calculus 1 stuff right here. Okay, so a couple other ones that I want to mention. So what about, well now let me go back to that point before I introduce the symbol. So given f of x here, we get a minus, a cosine of x. Okay. What's the antiderivative of that? So what function, capital F of x, has cosine of x being the derivative?
Sine.
What's that?
Is it a sine?
Antiderivative.
Yeah, I think. Wait.
It gives me sine plus sine.
Yeah, just positive sign, right? Because remember, derivative, right? Derivative of sine equals cosine. So we already have the derivative. Right? So going backward, I agree with you, Colin. Sine of x. Sound good? And plus c. Sound good? So yes, my intention here is to remind you guys. So a lot of these problems here we have to base off right from our previous learning, from our previous understanding from calculus 1. Right? So I'm going to come back to this table and again fill in that rule again. So yes, for the function here, and this is along the trig function family over here. So if you got cosine of x being the derivative, right? The antiderivative here come out positive sine of x, right? Okay. And of course, don't forget plus c. So in the short version, it means this is the one short version with the new notation I introduced here. The antiderivative of cosine of x in respect to x, right? That is that gives me the answer here: sine of x plus c. Sounds good. And then you see all these things being printed all over your books and being put in box, all that, right? So just like that. Again, what do we have for the other ones? Right, so what about when your function here is a minus sine of x? Then what's your antiderivative for that? Yeah, this is the positive cosine again. It's cosine of x plus c. That's just exactly the reverse of what we've learned from 172 calculus 1. Okay. question? So you can go ahead and extend that into our table there, one more line like that, right? So all of these guys are here, starting with this line, it's the trig functions. So minus sine of x, right? The antiderivative here comes out being cosine of x plus c. And that means right now we're writing that as antiderivative of minus sine x. That's one function right there. Textbooks even skip, a lot of textbooks skip the parentheses, but it's just I feel like I want to put that around the name of sine of x to indicate that parentheses is indicating containment, right? We contain something inside of that, so the whole thing in there is our main function, and then we take the antiderivative with respect to x. Good? And I forgot that the answer to that is cosine of x plus c. And then you guys, on your notes here, I'm running out of space, so I'll have to erase this and continue to extend my table like that, right? But on your work, you keep putting it down, further down on the rows again. Sounds good with that? Okay. And then let's do some more. So now for the whole class today, we're just going to explore all of those rules that we've learned like that. So you also remember that so now I'm asking you a 172 question here, calculus 1 question here. What's the derivative of tangent of x? I'm talking about the derivative and not the antiderivative. Yes, what?
Secant square root of x.
Secant square root of x. Okay, very good. And of course, these things right here, if you don't remember, that's completely fine. I don't remember that either, right? They're so common enough. So this is the part where, any Google website can tell you right then. It belongs to pocket reference, right? So you can, if you don't remember any time, just pull out that reference somewhere. But now I mentioned this because now you can see that if the antiderivative of secant squared of x, right? So that leads logically to our level now. Antiderivative of secant squared, surprisingly, is that simple function tangent of x, right? Plus c. See that there? Okay. So now for short, let's go back into that table. I still got enough lines to mention one more right here. But so right here, how I'm seeing it, when our derivative being secant squared of x, right? Then the antiderivative is going to come out tangent of x plus c. Very good. And then formally, as a rule, with the notation, right, we're gonna have to go. I'm so out of space right here, so let me write it this way. So something above that, right? We got secant squared of x. Right? Our function taking the antiderivative, giving us tangent of x plus c, and then formally with the symbols, it's this symbol over here of secant squared x dx comes out being tangent of x plus c. Sounds good. And then for the trig function, there's still more. There's like the antiderivative of minus cosecant squared of x, right? And so the antiderivative of that is simply going to give you just cotangent and all that, right? So basically, you grab a derivative problem that you've seen back in your Calc 1, right? Grab a derivative problem and think about the antiderivative. That's just the original function. So those are some of the basics. So there's still one more that's worth your attention right here. So let me erase them to make further space for ourselves here. I didn't get to a full explanation. I don't think I can get to a full explanation at this point yet, but it's worth it to mention. And then we'll head on to the explanation later as we move on toward the inequality. Okay. Now, so I'm making some space for that, ready for the next thing, and for you guys, just go ahead and extend your table further. All right, guys, tell me this. Remember this? From Calc 1. What's that? Yeah, e to the x, right? So the derivative of e to the x is that famous e to the x. Sounds good? So e to the x is really one special function like that. I mean, you take the derivative at e to the x. Now, guess what? What happens if you have an e to the x as the derivative already, right? What's the antiderivative of that going to be? Yeah, e to the x plus c, right? When your function is e to the x, right? Taking the antiderivative, it gives you e to the x plus c. And then the formal version, the antiderivative of e to the x, dx, right? Going to be e to the x plus c. Right? And then I promise I'll get into a formal explanation later. For now, I'm just going to write it down. And right now, you're going to feel like I'm failing to show you the explanation. But a lot of times, your exponential function comes with, so it's e to the x, but e to the ax, some coefficient with x. Yeah, see, we got more than one variable. Okay, but we target at x here being our main variable, the a here, now we're treating that as a coefficient. So if that's the case right here, right now I'm just going to tell you the answer as a rule right now, and then later on I'm going to come back to that and give you a formal explanation, and you should be able to derive your explanation at that point later on in the quarter. But now the antiderivative of something like this is going to be, yes, it repeats the a to the ex, I mean the e to the ax. It's just the nature of exponential function. You take the derivative, you take the antiderivative, it's always going to, the core thing is it's always going to repeat the exponential part itself. But now since it's got a coefficient here, right, the answer really is a 1 over a coefficient in front. Okay, 1 over a coefficient in front, multiplied with that e to the ax, and then plus c. Okay, so the rule that deserves your attention for now is that you got the e to the ax, right? Taking the antiderivative of this. So that's why now, see, I introduce it, I really emphasize this d thingy like that, because when you're in this situation, you already start seeing more than one variable is involved, right? But which one is the main variable for our problem right here? The x. Okay? And that's why with the a here, right, we see that just as simply a coefficient. Sounds good? So now, according to that rule I've just introduced without a real explanation, we got the answer to that is 1 over a times e to the ax plus c. Look good? All right. So now this table for now should be enough with some of those basic antiderivatives, some of those basic rules. And then there are still more rules waiting ahead for you guys. Now we're still looking at antiderivatives, but as a subtopic of that, let's look at the rules, some more rules, right? So earlier those are just basic rules, and they're pretty standard on their own. But now we're going to look at some more rules. These are, I would say, these are the universal rules. Okay. Because those rules you've seen on the other board that we wrote down, those are more like the specialized rules. Okay. They stand on their own. Here, let's look at some more universal rules. So here's the thing. Let's say that, the number one thing I want to introduce. What happens if, just a developing problem right here, if you're given 5 dx. Okay. What is this telling you as an instruction? This is a problem, right? You're given that problem, but what is the problem telling you as an instruction right here? Find the antiderivative of 5. There you go, in respect to x, right? So that means in the way how you're reading this notation right here, you understand that your function here, explaining the role here, is a constant function. You guys following? Okay? Alright. And so now, there you go, start your hunt. Start your hunt. Because really there wasn't really any methods yet, right? So if your function is simply a constant, and that constant being treated as the derivative, so what antiderivative are we looking at here?
5x plus c.
Yeah, 5x, right? Plus c. You guys see why? Your friend here suggests 5x plus c. So why is that? Because being the derivative here, I mean, it's 5 times x to the 0. You guys follow me on that? Because just the constant, it means that 5 times 1. And 5 times 1, you always see this. Initially, it means means a 5 times 1. But this one right here, you can think of that as x to the 0. You always have your choice of thinking of that as an x to the 0. Yeah, that. But how do we know it? 5x plus c is the derivative, is the antiderivative to that. Take the derivative. Take that derivative, right? And we land right into, see, constant term gives me a 0, that gives me a 5, and that's why it's 5. Okay? I also kind of mentioned that one only way to check your answer anytime you find an antiderivative, take the derivative. Right? Anytime that you come up with an antiderivative and want to make sure that that is your answer, right? Take the derivative of your final antiderivative. And then if it was a correct one, it should give you back that beginning function, that derivative. And so yes, antiderivative of 5 being a constant gives me 5x plus c. So what did we observe here? Now, so what if I go outside of 5, but generally as a constant c, right? A constant c, and then with d being right there. So taking the antiderivative generally of any constant, it really gives me just cx. Okay? The constant right now, the antiderivative version becomes just a. Guys, can I change to a different letter? Because I already use C, and sometimes it's hard to differentiate, to make the distinguishment between the C and lowercase c and the uppercase c. So you constant k. Taking the antiderivative gives you simply just kx plus c. So that is one rule for now to know already. Anytime you take the antiderivative of a constant function, right, it gives you just kx plus c. Sound good? All right. The journey is still long here, but for now, constant. Sorry, I was writing C for constant, that's why. Right, so that gives me kx plus c. Agree? Now that deserves a special rule on its own, right? And eventually we're going to put these rules together, and that will become a method for us. So now, there's a little impact here, what you guys need to understand. A lot of times, starting this point right here, you will understand it even better later on as we go on the quarter, but this symbol over here, yes, I've been telling you that we treat it as one package, the symbol here together with dx, right? But now, it's a little early to tell you right now, but the relationship between the function here and that dx, right now think of that as a product. Right now think of that as a product. That's the function multiplied with that. Where the symbol, it's not really a quantity or anything like that. And later on, I'm going to explain why it is a product. But you can right now kind of cheat around and think of that as a product between the function and that. So why am I saying that? Because with this rule we have just learned, yes, it means a k times dx and all that, right? So in the worst case, you have just something like this. Your textbook writes things like that all over. Which is that's one dummy symbol and with the dx. You don't even see the function at all. Okay? Where's the function? The truth behind the scene now is it means 1 dx. Okay? It means 1 dx. Okay? And the reason I have to mention a little bit about, I have to cheat around a little bit about its multiplication, because if you don't see anything right here, it means a 1 times that. And so your function is a constant 1. Okay? Your function is a constant 1. Now with this rule right here, it's easily just x, right? 1 times x plus c again. Right? But then why is it a product between a function and that dx? I will save that explanation for later, because right now we're just very at the beginning of our journey with that. Right? At some point, if I'm turning on the green light for you guys, it's okay to cheat here, then yes, we can cheat a little bit. But otherwise, most of the time we stay aligned with the proper order of how we learn these things. Sound good? Okay. All right, so take a good note of that. Right there, you see this kind of weird antiderivative problem. A lot of times, antiderivative, something like that, it means you take the antiderivative of the function 1, right? dx. All right, so another rule is that's worth your attention. Now, when you have a function, but then that function comes with a coefficient c in front, lowercase c. A lot of times like a 5x squared plus, like a 5x squared right here. Okay? It's really the x squared right here is your f of x equals x squared. You know what I'm saying now? I mean, needless to say, the whole thing is a function, but I'm talking about when you're looking deeper into the actual anatomy of that function right there. It comes from some core function, and then multiplied with a coefficient. See what I'm saying now? Okay. And so when we're in that situation, your function that you're finding the antiderivative comes from some core function, and then with a constant coefficient. Taking the antiderivatives here, okay, gives me just, well, you find the antiderivative for f, just for f, and then you multiply that constant coefficient back, and then plus. See, that's the difference between the small c and the big C, right? The rule that's when your function appears to be having some core function with some coefficient. So some quick impacts here, some quick example. This is not even a formal one. This is some quick little example to think about now. See, I said it earlier, 5x, right? Square, the antiderivative of this. Your function is a 5x squared. Yes, that whole thing is 5x squared. But the way how I'm seeing this now, it's some function x squared, right? How a rule can be used here. See what I'm saying now? How rule can be used, and then there's a constant coefficient 5 in that. And so now we can pick things up on the fly here. You only need to worry, so your power rule allows you to, hey, the antiderivative of this thing is going to be an x cubed times 1/3, right? The antiderivative just on the x squared goes right into the 1/3 x cubed. But then there was a coefficient 5. So this rule right here is telling us that, hey, multiply 5 to that. And then let's see. And that's why the overall answer now is a 5/3 x cubed plus c. So it seems like I'm slowing you down for that, but the point now is that, and of course, when it comes to learning this, a lot of times you feel like it comes very natural. Yes, let it be that way, but I still need to, as an instructional purpose, yeah, right? I still need to show you where it came from. What really was a rule that allows you to think that way. You know what I'm saying? Yeah? All right. So, and now with that rule we've just previously learned, there's another rule right here. And then at this point right here, I don't even want to number them like rule number 1, rule number 2, or whatsoever anymore. Okay. So, think about a problem like this. Now you got x cubed plus the x. Think about a problem like that, right? That's a demonstration problem that you want to find the antiderivative of a function. But now your function got 2 terms, right? Well, 2 terms of that. Okay. And so when you're in a situation like that, yes, there's a rule. You can do the following. You can separate it out, see, because 2 terms here, so that means each term in your function is one middle function. So you can think of this as some f of x, and this other one right here is some g of x. So your entire function that you finding the antiderivative here, it is the sum of some 2 terms. Yeah. And each term individually is a function. And so naturally enough, I'm going to let your brain fly here a little bit. Yes, it's naturally enough if you do one separate one for x cubed. See what I'm saying now? And do another natural one for x squared. Okay. It makes sense that way, right? And yes, I agree. So the answer would come to, what's the antiderivative of x cubed? Yeah, that rule, that power rule we've learned is a 1/4 x to the 4th. And then that guy right here is a 1/3 x cubed, right? But then what do we do between these guys? We add them. See what I'm saying now? Okay. And so, what was that rule that we drew out right after this particular problem we did? It promoted the following rule right here. What you got? Your function being multiple terms. Each term is a function of themselves, right? And these 2 terms, right here, I demonstrated with a problem where it was adding between the terms, but it's also included a case of subtracting between the terms as well. So when your function is like that, right, multiple terms, then taking the antiderivative, right, you are allowed to do each term by each term individually, and then add and subtract depending on how they started out at first. So here you can do one separate antiderivative for f, okay, one separate antiderivative for g. Okay. and then you add or subtract the two results according to that, to how it began like that. Right? So many textbooks refer to this as this rule right here. A lot of textbooks refer to this as the sum or difference rule. The rule to take the antiderivative on a sum or on a difference. I'm going to have to yell really out loud right here. This is about the end of our universal rules. Okay? Back in the days of finding derivatives, you have what's called a product rule, right, and a Volch rule, right? Okay, so something like this. If you got like f of x times g of x, and you want to find an antiderivative for a product right here, this is really good luck. Okay, we don't have any rule for that specifically. It's a little bit unlike the days that we were taking derivatives. Derivatives has a rule specifically for products, but antiderivative, we don't have any rule for a product. See what I'm saying? That's why I'm saying good luck. So that means there's no such thing as a as a product rule for antiderivative. Okay? I keep having students all over my time teaching that all of a sudden give me a problem that they were doing this to me. This antiderivative becomes the antiderivative of f times g. Okay? And then plus they try to mimic, they try to copy that way how they were doing the derivative rule, and then doing the f itself right here times the antiderivative of g of x. This is really way out of focus. That's not how it's done. Okay? So as a matter of fact, good luck finding for a rule with that, because there isn't. Sound good? Okay. And then if you're starting out with a function, and you are asked to find an antiderivative, right? There's no function rule. That's what I'm yelling out loud to everybody. Okay. So don't use your function rule similar to the way you've done it back then in Part 1 and then apply it here for antiderivative. And attempting that it's gonna and try to believe that it's gonna become your actual antiderivative. It's not. Okay? And you always have your way to check. If you really were going this route, right, check your final antiderivative by checking the derivative. Will it land into the beginning of the product? I don't think it's gonna do so. Okay. So now we're gonna put ourselves into a more of a combined kind of problem here. So let's call it that. Two. If we wanna. Find a very short instruction. And then what we want to find here is part A. Find the antiderivative of this function. So how about 4 minus x to the 4, 10x to the 4. X minus 1 over x. Okay. So let's look at something like that. So for something like this, so the first thing I'm seeing now is that again, this symbol here altogether as one package symbol, right? It's telling us that yes, we want to get the antiderivative out of that function right there. Okay? And so in this way right here, the sum difference rule basically allows us to find that antiderivative because our function here got multiple terms, right? So now we are able to find the antiderivatives term by term here. So formally speaking, you can go and right now, because again, I'm trying to set that foundation for everyone, so we try to align ourselves with the rules here, but then eventually when you advance enough, right, then I can start going loosely with these side-by-side rules here. But the first one here is the constant term. So you're going to have to find one antiderivative for that. You guys follow? Okay. And then the next one here is going to be the 10x to the 4th. We need to find one antiderivative for that. Okay. But now it connects with the earlier term by the subtraction. Right. And then the next one here is an antiderivative separately for 1 over x square root of x. And then it connects to the earlier terms by the addition. Okay? And And so just like that, and then now we're going to have the antiderivative for 1 over x, right? And then connect with the earlier term by that, forget. Okay? And so I just want to mention that, see, let's just pay a little closer attention to this sum or difference rule right here. Because the idea is, yes, we are allowed to find antiderivative individually on each of the terms here, correct? But you didn't need to dump in the constant c in each of the little ones here, and you only need to add one overall constant at the end once you found your final antiderivative. Okay? Technically, there's a little C1 constant here, and C2 constant, and C3 and C4, depending on how many terms we got, right? But then in the end, they all are just going to add up into one general constant. That's what allowed it. That's what we are allowed it for. Okay. And so now, at this step right here, I just want to point out that we have just applied a sum or difference rule right here by breaking it down into multiple separate antiderivatives for each of the terms. And so now, I'm going to need to use the other board right there. And the work is going to become easy this time. And all of the little rules, now we can put all the pieces together. All the pieces that we've learned, it's going to pay some good contribution in here. The first term right there, the first antiderivative there is going to be a 4 for x. Because we've learned that based on that rule right there, that I'm still reminding you guys. See that now? Okay, and then there's it's going to subtract, right, the antiderivative for the next term. So pay attention. This antiderivative here is indeed, we got a core function being the x to the fourth, right? It's a power function right here. Okay? But now, see, as a quick explanation, the 10 x to the fourth dx. And that core, what I'm talking about is really, the power function is here. We can apply that rule. But then you can treat that 10 right here as a 10 and then times the antiderivative of x to the fourth dx. Right, so that's a little bit of scratch work right there. So quickly, this overall antiderivative becomes what? We got 10, right, times, and then now 1/5 times x to the 5th. You guys agree with me on that? Yeah? Okay. And so now I'm going to put that result together. And by the way, you guys are advanced enough to see that 10 cancel out with 5, right? But maybe for now, I'm just going to write the whole thing, and then we're going to clean it up later. So 10 times 1/5 x to the 5th. That takes care of the second term. And so now the third term, remind yourself again, the third term from the other board, the function was a 1 over x square root x. Okay? And so now that's why we have that example earlier in the earlier lecture that we learned a little bit of how we can manipulate the algebra, right, into solving these, into handling these problems. And so you can think of this algebraically, this function here as a x to the minus 3/2 power. You guys agree? And so the arguments, the reasoning that leads to that is very similar to that. Those are example problems I've delivered in example 1 that we've done previously. Okay, so we built our skills on top of those. And so now the antiderivative here is going to come out really x to the, so minus 3/2 plus 1, right, on scratch work like that. And then 1 over minus 3/2 plus 1. That's how we on that again. And then I don't need the little constant c at this step yet. Alright, and so think about on scratch work here, what's minus 3/2 plus 1, by the way?
Negative 0.5.
Yep. So it's going to be x to the negative 1/2. I recommend writing that decimal as a fraction like that. Okay? So it's going to make it overall minus 2. So the minus 2, but then your term here was adding, so we got add, and then minus 2 times x to the negative 1/2, right? And then the last term here on the other board, the last term was a 1 over x. So we knew that rule by heart at this point. It's just going to go straight into natural log of absolute value of x. Right? And so in that case, I'm going to put that term into our function, and it's connected to the other terms by the subtraction. So minus natural log of x. And now we have taken care successfully of all the terms, right, in terms of finding all of the antiderivative. And now we're going to go ahead and put our final overall constant plus c in that. And now in the next step, it's just a matter of cleaning up the coefficients a little bit. So 10 cancel with 5, that's 4x right here, minus 2, right? X to the 5th right? And then the combine the signs are here, making it minus 2x to the negative 1/2, okay? Minus natural log of absolute value x plus c. Right? So we came to what we thought, right, to be the antiderivative of the entire function from start. Yeah. Now, once again, I want to bring back something I've mentioned, but this time let's enforce that really. How do I know if I have done the work all correctly? Or in other words, how do I check for my final answer to make sure it's correct?
Roll it back.
Yeah. And what do you mean by roll it back?
Just derivative it again.
Yeah. Just take the derivative of this thing right here. Right? To make sure if once you take the derivative here, as long as you land into something that's exactly the same as that, right? And then, then we know that we found the correct antiderivative. See what I'm saying? Otherwise, so it's not a requirement to write it on your work, but when you're working on scratch paper, make sure you do check. Okay. So 4x minus 2x to the fifth minus 2 x to the negative 1/2 right there minus natural log of absolute x plus c. Take the derivative. That's how we do. Okay. And then so first term is yes, comes out to be a 4. Next term is a minus 10x to the 4th, right? This power rule multiplies down. And then the minus 1/2 multiply with that, right there, cancel out and make the negative sign into a positive. So it's plus x to the negative we have power. Okay. You guys follow me on that? Okay? And then the minus and the natural log right there goes into 1 over x. The constant term goes to 0. So now this is a successful beginning one. Right? So now we can go ahead and legally put our final answer here in the box, indicating that it's our final answer. And I said it out loud yesterday that in the world when we're doing antiderivative, yes, we are undoing derivative. We are doing some work that's related to derivative, but all of a sudden the product rule that we used to know from derivative doesn't exist. Right? In the world of taking antiderivatives, the quotient rule as we used to know it doesn't exist, and see what I'm saying? No? And so, but the worst case is here. A lot of times you're being given problems like this. So you want to find the antiderivative, right? Now let's say you got 4x to the 6 minus 5x squared plus 1, something like that. Okay, and then we go divided by 2x squared. Okay. Actually, let me change. I'm changing my mind a little bit. 2x cubed, how's that? Right? Dx. So the whole symbol, that symbol here with the dx is one package of notation. But the main function we're looking at is this ugly looking rational expression, right? That's quotient right here. You guys following that? Okay. All right. So for something like this, again, remind yourself, no quotient rule. The reason I have to mention this is because it does look like we are having a quotient right here. No quotient rule, or no equivalent quotient rule, no product rule. So don't do things like that. Don't try to brutally apply the product rule. Similar, try to make it work similar to the days you're doing derivative, right? So if you don't have these rules existing, what can we do? At least the algebra is still working here. So you will never get away from the algebra. You gotta get your algebra going again.
Just take it apart.
Yeah, take it apart. So at least the good news here is that we got one common denominator here. So now I'm talking about the algebra before the actual antiderivative work right here. That's why the symbol here remains. See what I'm saying? No? All right. So breaking it apart, you can go that into one fraction, right? Making it, and you guys are advanced enough. You can go ahead and go skippy on that a little bit. 4x to the 6 cancel with 2x cubed, right? Making it 2x cubed. Again, you guys following? Okay. And then the middle term with a subtraction sign right here, looking at minus, right? We've got a middle term right here. Sounds good then? Okay. And then that goes, so 5x squared over 2x cubed. Again, that gives me a 5/2. Yeah, from 1 over x. I prefer to write it that way. Even though, yes, you can write it as a 5 over 2x, but I write this for a reason. And then the last one here is a plus, right? And then there's, yes, your term there. And my board is admittedly getting a little busy, but I hope you see the idea right there. So now we broke it down into multiple terms. 1 over 2x cubed Now we've got 3 terms. Sounds good? And that's the only way, really, the only way how we can get around more or less. Because the problem right now is we don't have the quotient rule to work. And there has never been a proven quotient rule. All right, so now at this point right here, and again, what I have done on the other board there was simply just the algebra work for that, right? And then you have had some experience earlier, so now we can start picking up things on the fly over here. First term is going to give me, okay, so I'm not going to beat around the bush anymore, but first term is going to give me a 2 times a 1/4 x to the 4th. You guys agree? I'm taking the antiderivative, and I don't need to bother spending out the time writing down each antiderivative step anymore, because this is already the antiderivative. And then minus, and then the next one there, it's going to be a 5/2 isolated out as a coefficient, but multiplied with the natural log of absolute value of x. Agree with me on that again? Okay. Minus, so I'm going to kind of combine signs together right there. Anyway, so minus 1/4, right? X to the power. Okay. Plus c. Right. And so at this point right here, we can just kind of clean up the terms a little bit so that it's making it half x to the 4th, right? Minus 5/2 natural log of absolute value of x minus 1/4 x to the -2 power plus c, right? And then once again do your checking of the derivative, right? Make sure you check. So 1/2 x to the 4th minus 5/2 natural log of absolute value of x minus 1/4 x to the -2 power plus c. Now, if you take this derivative, are we getting back to that beginning function again, right? And so that first term right there is giving me a 2x cubed. That does look like the first term already. Minus, and now this gives me a 5/2 1/x, which does look like the second term. And then the last one right here is a minus, but then multiplying this -2 down right there, it's giving me a plus, right? 1/2, and then x to the -3 power. And then, so now that's completely, aligned, right, with the beginning function again. So now you know that you have found the correct antiderivative. Right? Taking the derivative of that constant c, of course, goes to 0. So it's impossible for me to show every problem out there where you have to bring in the algebra experience. So you've got to definitely rely on your algebra. The point is, try to look into it to see anywhere that you have to apply the algebra before you advance into the actual calculus work. Okay, so antiderivative, I so call that the calculus work. But then the algebra, cancellation things out, simplifying the expression, breaking things apart like this, that's all the algebra that you got to take steps before the calculus. Sounds good with that. Okay? All right, so let's do another one. We can still got some other problems there where I want to show you some more experience. So again, as a reminder, no quotient rule or no product rule to be similar to those in the derivative thing. So same example, part C right here. What about let's find an antiderivative for the following function. And you know what? Seriously, I'm getting tired of dx, so why don't I try to switch over to dt, right? So that means do expect that your function is going to come in the variable of t. Okay? The point is, see the d that I explained from the earlier lecture, right? The d thing here has to match, right, with that variable's name like that. So let's say we got t squared plus 1, and then in product with t cubed minus 3t plus 2. Right? So you've got something like that. And we're taking the antiderivative in respect to t. So just like that, I just now clear out the board to make space, but that same note, that same reminder is applicable here. Again, we got no product rule, right? Because what I see here is a product between some two functions. See what I'm saying? No? So how do we handle this?
You sub t squared plus 1 equals u.
No, that's way into the.
You could do that though, makes it much easier.
What's that?
You could do that though, makes it really
Yes, but I want to save that for some formal stuff later on.
Yeah.
It's actually some formal real good method that we want to take some cautious learning in that.
And I guess right now just expanded?
Yeah, that's all it does. Yes, expand it out. Okay. All right. So don't worry about making any substitution or anything like that yet. And right now it's just the algebra work. So antiderivative, what do we have here? T here, right? Minus 2t cubed plus 2t squared. And we need to move this a little further out. Plus t cubed, so that's making it minus 2t cubed. Okay? Minus t plus 1. Okay? Fair enough. Did I do my algebra correctly? What's that?
It should be a plus 2.
I agree. It was right in front of me. I don't know how I missed that. All right. And so now at this point, and that again, that's just the algebra, right? And so now we're ready for, and my board here is now having enough space for me to write the work right here. So it's gonna make it what 1/6 t to 6, right? Sounds good. And then now it's gonna be 1/2 minus, by the way, minus 1/2 t to the 4th. Three again. And then plus 2/3 cube minus a 3/2 t squared. Now it's going to be a 2t. And the last one here is a 1c. Okay. And then here you guys have done fluently. And hopefully I hope I got you into that habit, because a lot of time for the rush purpose in instructing in class, and I have to make it as fast as possible. So I tend to skip the checking, but that I don't want you to get into that habit. Okay, when you guys doing your work, make sure you do the checking, because you guys are learning. Okay, all right. But yes, I believe the answer here is already correct. Okay. But that's how we handle. So at this level right here, please don't think anything fancy yet, okay? Because I want to save that good stuff for later on, when we have some really formal learning. Because once you get that later stuff correctly done, then it will carry into your Calc 3 and Calc 4 stuff as well. It's not just something to be able to do this. There's a little thing here that I want to share with everyone. It's just experience. But I want to make sure you guys also free from this kind of error right here. Let me just create an improvised short antiderivative problem right here. So the problem here that I'm about to introduce is, it's not part of the example, by the way, but think about this. So I already mentioned that, say something like this, okay, is an antiderivative problem, right? Okay? It's instructing you to find the antiderivative on that function 5y plus 3, right? And taking the y variable here as the main variable. Sounds good with that right there? And then yes, you do your work, and then you come up with a 5/2 y squared plus 3y, okay, plus c. Is it correct to still write this? Okay. So make sure you recognize that it's incorrect to still remain with that symbol here. Because over time, I don't know why, over time when I'm teaching at other places, I keep seeing students at some point, they know what they're doing, but they still mistakenly attach that symbol here. Because the point now is that the symbol means an instruction, right? And we already found the answer to that instruction. Am I making sense? So that means we no longer carry this symbol at the answer level. Does that make sense? No? So make sure you stay away from that mistake, okay?